We're going to try to take one.
Rolling. Frame.
Okay. Ready. Okay, keep rolling. Hi. Wait, wasn't ready. I'm going to start that again. So here I go. Okay, there's no denying the effects of global warming on our planet. Countries around the world have been experiencing record temperatures for years, but none more pronounced than right here in Antarctica. Five years ago, the idea of swimming in Antarctica was not only ludicrous, but actually impossible, because most of the shoreline water was frozen. However, as you can see over my shoulder, the water is not frozen. And the temperature today is a balmy 8 degrees Celsius. And to me, that sounds like a good temperature for a swim. Okay, we'll see you in a bit. Well, after witnessing the devastating effects of climate change on Antarctica, we decided to report on the latest scientific discoveries at both polar regions.
So come on, let's go.
And we're doing this because, once again, the United Nations has invited us to show our film and share its findings with delegates attending the Climate Change Conference this year in Cancun. The polar regions are the most remote places on Earth, and as a result, films like ours are sometimes the only way people get to experience these often beautiful and always fragile ecosystems. Hey, John.
Hey, nice to meet you.
You know, historically, polar scientists have always had difficulty getting their research out to the world. And we're hoping this unique journey opens the eyes not only of environmental policymakers, but of the average person who never gets the opportunity to see these remote places and experience the devastating effects of climate change firsthand. There's a real and legitimate sense of urgency here, because according to NASA, the polar regions are the fastest warming parts of the planet. This is why the scientists come here. This is why we need to be here. This is the goal of the Polar Explorer. After 5 flights and 3 days of travel, we finally reached our destination and boarded the icebreaker Amundsen.
This is much more comfortable.
Just getting to the Amundsen has been exhausting. But in reality, our journey has just begun.
To a different floor. We have to go around.
We're going to be crossing the fabled Northwest Passage, a route that has long been the goal of explorers dating back to the 1400s. We'll be starting here at Sachs Harbor, then crossing through the seldom navigated Prince of Wales Strait. We will then cross over and proceed north to latitude 76, before returning south and ending our journey here in Iqaluit. During the course of our expedition, we'll be talking with the polar scientists of ArcticNet, as well as members of the British Antarctic Survey team and the various crew of the Amundsen. Our ship gets its name from the famous Norwegian explorer Roald Amundsen. It was Amundsen who was not only the first man at the South Pole, but the first man to reach both poles in the same wooden ship. And he was also the first person to cross the Northwest Passage in 1906. It's amazing to think what will take us less than 3 weeks took Amundsen 3 years to cross. At the time of his crossing, Amundsen wrote this: "It is in the service of science that
These numerous and incessant assaults have been made upon what is perhaps the most formidable obstacle ever encountered by the inquisitive human spirit."
Tomorrow, we begin our crossing. I can hardly wait. Today it's Saturday, October the 9th, and so far I've been really surprised at how little ice there's been here. But we've just been informed that the first signs of ice are now starting to appear. So we're heading up to the deck to check it out. All right, here we are on the starboard side of the Amundsen. We're just about to enter the Prince of Wales Strait, so things have really kind of picked up here. The weather has picked up. We do have some wind now, and we have some snow, as you can see. And what we're passing through, you can see over the side here, is some very thin ice. This is known as new ice. It's almost like pond scum. It's very thin, very fragile, but the ice flows are starting, and we're going to be charging through them as they get a little thicker, and we start to encounter older ice. Now, a lot of the ice here is 1 to 3 years old. That's actually pretty young for old ice. Usually the ice around here is 7 to 10 years old, so it's actually melting a lot more, and so the old ice we're encountering is a lot younger. Actually, one of the main reasons we wanted to come to the Arctic was to report on the melting of the sea ice and its impact on the ecosystem. In order to get a better understanding of exactly why this is happening, we talked with climate change scientist Dr. Bruno Tremblay.
As of now, what we've seen from satellite measurements that were started in the late 70s, so we have about 30 years of measurement so far, always using the same instrument, so it's a consistent data set. We're seeing about a 10% decline in ice areal extent per decade, which means over 30 years, it's about 30% loss of Arctic sea ice.
According to the National Snow and Ice Data Center, ice extent has shown a dramatic overall decline over the past 30 years. During this time, ice extent has declined at a rate of 11.2% per decade during September, and about 3% per decade in the winter months. In these satellite photographs provided by NASA, we can see this loss of ice over a 30-year period. As of January 2011, the Arctic recorded its lowest amount of ice coverage since satellite recording began in 1979. More than 50,000 square kilometers less than the previous record low, set in 2007.
In the winter, the ice expands and basically reaches all the way to the continent, and at this point it cannot go any further south. So basically, in the winter, you see much less of a signal, because the only place where you can actually lose ice in the winter is in the open channel of the North Atlantic and also in the North Pacific. So there the signal is less drastic. But there's two things that we need to look at here. It's ice extent, which means the area covered by sea ice, and it's also ice volume. And so the thickness of the sea ice in the last 30 years have also declined. Thinner ice melts faster, it opens water more readily. So because if you have a little bit of melt, you will uncover some of the open water. The sunshine will actually warm up the surface ocean, and then there's a whole feedback taking place. You warm up the surface ocean, you melt more ice, you have more open water, more sunshine being absorbed, and it's a positive feedback. And then you can actually lose a lot of ice very quickly. And even in the recent 2 or 3 years, when the sea ice extent have actually grown again with respect to 2007, which was the all-time record minimum, but during those 3 years, the sea ice volume has continued to decline. So we've lost thickness, even though we've gained in area in the last couple of years. So only looking at ice area extent is a little bit misleading, because you might have what looks healthy sea ice cover, but it might actually be very thin.
So we've been on the Amundsen for a couple of days now, and we haven't encountered any substantial sea ice to speak of. Now, I have to say I find this a little disconcerting, to think that the Northwest Passage, while previously frozen and considered almost impenetrable by explorers, has for us been mostly smooth sailing. Looking out over all this open water, I can't help but wonder, is Antarctica experiencing the same kind of loss? Historically, Explorers like Sir Ernest Shackleton faced many challenges navigating through its traditionally frozen waters.
We reached a point within 97 geographical miles of the South Pole, some days spending 12 hours doing 3 miles. We made many interesting geological and scientific discoveries and had many narrow escapes throughout the whole time. I, Ernest Shackleton, have today, March the 30th, dictated this record.
Today, scientists are employing the latest technology in Antarctica to better measure the sea ice, as Ted Maxim of the British Antarctic Survey explains.
The main thing we want to do here is be able to get a better idea of what the thickness of the sea ice is in the Antarctic. In the Bellingshausen Sea, it's been decreasing quite dramatically. In fact, as dramatically or even more so than sea ice extent in the Arctic. Most of the ice we see around us is stuff that grows and disappears every year. It's what we call first-year ice. It's seasonal ice, stuff that only sticks around once a year. Now, the ice isn't just a level sheet like you have on a lake. It's also quite bumpy and ridged, and that's because it's a very dynamic environment. You have blocks of ice being pushed by winds and currents and creating these big ridges like these ones we have behind us. And so that's one of the things we want to find out down here is when we look at it from the surface, we see all these jumpable blocks. But it's pretty hard to see what it looks like underneath and how thick it is. And that's because it's really hard to drill through this ice and get the thickness. So what we have here is we've got this robotic submarine going underneath the ice. It's going to look from the bottom, it's going to give us a 2D map of the underside of the ice. And what we're doing on the surface is we're getting a 2D map of the surface of the ice. We'll be able to relate those two things together. And from that, we'll be able to interpret what satellites are seeing from space of the surface, and then get a better estimate of the total thickness of ice we see here.
This is kind of important because most of the measurements we make of ice flows are made by satellites, which get the surface view. But we don't really have a good sense of what that surface view corresponds to underneath the ice. By going out on this expedition, what we hope to do is try and understand the statistics of the surface versus the underside of the ice, and use that in the context of satellite measurements to get a better understanding of what sea ice and sea ice thickness is all about. So sea ice is essentially the canary in the coal mine. As the sea ice is disappearing, we have a good sense of what's happening to the rest of the planet.
With our journey relatively ice-free up to this point, we decided to talk with a veteran icebreaker captain, Stéphane Julien, to share his opinions on recent Arctic sea ice conditions.
The question is not will we have ice in the Arctic in the wintertime? I guess this is a given. It's just the survival of multi-year and the polar ice cap so could it be that at some point the Arctic become like the St. Lawrence Gulf, totally ice-free in the summertime? This is what the scientists are looking into, and this is what they're trying to find. And if so, when? How fast is it going to get to that point? And what effect will it have to the rest of the planet? The ice cap has been there for over 1 million years, resisted all the glaciations and then glaciations melting. It was always there in the summertime. And within 100 years, it will disappear.
The Amundsen is a sophisticated science research vessel, and as such, will be stopping periodically at several stations along the Northwest Passage. Stations are designated stops that allow for specific research activity. Today in particular, we're collecting numerous water samples with a high-tech device known as a rosette.
We're just sliding in all the canisters of the rosette into its little garage. Data that are collected from the bottom of the ocean will be extracted and brought to the lab for further study. What we're looking at here is a series of graphs that indicate the measurements taken by the rosette that we just pulled up. It was down at 500 meters, and there's lots of different colors here, but what we're most interested in is the blue one, because the blue one indicates the water temperature here in the Arctic Ocean. And you notice here, from 40 down, It's, you know, between -2 and -1, kind of where it should be, and that's the lower water. But what's significant here is above the 40 measurement, we have a real spike in temperature going over 2 degrees. That's the surface water. And the temperature of that has been increasing quite a bit, where they've indicated an awful lot of heat transfer in the upper layers of the water here. So as you can see, this is really highly indicated by this spike right here.
In addition to the data provided by the Rosette, further analysis of the Arctic seawater is done in the ship's lab by seawater nutrient analyst Jonathan Gagnon.
This is called an autoanalyzer. We use that to analyze the nutrients that are in the seawater samples that we collect from the Rosette. First thing, I remove all the phytoplankton from the water using filters and a syringe. And I pour everything into small tubes. Then I bring everything back into the lab to get analyzed by this autoanalyzer. Every chemical in here is sucked in the system, and everything is mixing up into those coils. Everything is added, mixed, processed, and the chemical reaction begins and sends a signal to the computer, and therefore I can look at my chromatograph and I will have my results. We're analyzing nitrite and nitrates. The color will be red, kind of purple between the two colors.
The pink coloring indicates a lack of nitrates in the upper seawater, and these measurements indicate that there is less salt in this water, a clear indication of the addition of fresh glacier water entering the Arctic seas. After studying the depths of the water below us, we now turn our attention to the skies above us. Storm and sea ice researcher Matthew Asplund is giving me a lesson in weather balloon launching.
Okay, well, I'm about to do my 12 noon, 1800 GMT time balloon launch off the deck of the Amundsen here, the heli deck.
Okay. So what do we need to do?
Okay, so what we need to do is I'm going to put this on the nozzle. It's very straightforward.
Okay.
Usually to have a clamp, I just use my hand, get real tight like that.
All right.
Make sure there's no kinks in the hose.
Okay.
There it is talking.
Oh, sorry.
Okay, we're going to do it now.
Okay.
And then, so I have my assistant Joanne back there. She's operating the helium. Open the valve.
These balloons are launched every day to provide atmospheric data across the Arctic with respect to climate change and storm frequencies.
Nozzle down. So now I need to fold this over.
After filling the balloon with helium, Matthew attaches an electronic device that records and transmits data related to temperature, humidity, and pressure.
Okay. So what do I walk over to the corner of the deck there?
All right. We're going to launch this weather balloon. This is the sensor on the bottom that'll feed back all the data it records. After it reaches a certain altitude, we're going to be letting go of this soon. Okay, you ready?
Yeah.
Okay, here we go. Launch it.
The data received from these balloons has reached Matthew back in his lab in Manitoba. He reports that this reveals a trend to larger and more intense storms in the Arctic, which he believes to be linked to sea ice decline.
How high will it go?
Usually they get up around 20 to 23 kilometers, although I did have one go up to 28 kilometers on this trip. That's low to mid stratosphere. It's pretty high.
Great. Okay, there we go, guys. History in the making.
Today we're going fishing, but not in the traditional sense. We're going to be deploying a series of nets and a metal trap to capture marine life of all sizes. With the retreat of sea ice, new areas of these Arctic seas are now accessible for this kind of research. And the additional sunlight now penetrating these waters is doing something very unusual. It's providing increased photosynthesis to the flora here. That's the seaweed you find at the bottom. Now this in turn provides an increase in food supply for the fauna.
think this has a lot of consequences for the ecosystem. The loss of ice or the thinner ice impacts the ecosystem in many ways. It lets more light penetrate, and this light is essential for the organism at the bottom of the food chain, the phytoplankton, that synthesize organic matter for the food web. So by getting more light, they are able to produce more of that material to a certain extent, and they will also produce it sooner in the season because they get light very early on. So it's like if spring was coming a month earlier than it usually does. So this has a lot of consequences for the timing between the consumers and the producers, and also for the amount of material that's available for the food web. We see more in what we call exotic species coming to the Arctic.
We've seen how the melting sea ice in the Arctic is contributing to the growth of marine life, but is the same phenomenon taking place in Antarctica? Here, the loss of sea ice and significantly warming temperatures have resulted in an ocean environment that is fast becoming inhospitable to the native krill. Krill is a small shrimp-like creature and is very sensitive to the increase in water temperatures. Warming temperatures here make it extremely difficult for the krill to reproduce. The lack of sea ice has taken away the krill's sole food source, phytoplankton, a microbial creature that lives underneath the sea ice. And now, as the ice disappears, so does the food supply for krill. As a result, the krill population here has dropped by 80% in the past 40 years. And while this impacts directly on the krill, it also has a devastating effect further up the food chain. All creatures in Antarctica, penguins, seals, whales, eat krill. And now that their food supply is diminishing, so are their population numbers. On the West Antarctica coast, where 40% of sea ice loss has been recorded in the past 25 years, the populations of the predominant penguin species here, the Adelie, Chinstrap, and Gentoo, have declined by as much as 66% since 2004. It's just after midnight, and we received a call from Dr. Frederic Olivier. He says there's something we should see. So we're making our way to his lab now, and we're trying to be quiet so as not to wake the others.
I'm looking for, see, that's fun. You don't see anything, it's just mud. And then if you just go in, you find a lot of things.
As it turns out, the scientists have collected an unusual amount of biodiversity for this area.
So Nick, is this exciting?
Yeah.
What's going on tonight and why is it exciting?
Yeah, it is very exciting because we have sampled a lot of organisms. It is very rich with many Gorgonocephalus and many species. So we are very happy, and we hope to have perhaps the same thing in the next station.
But then you need to clear them. You need to clean them up a bit and then see how many stuff there is. Worms, shrimp, sea star, sponge, everything. Did you see it before? No.
Anyways, we're all very excited here because we just found a whole bunch of stuff in an area that is usually covered with ice, but is not covered with ice right now. So we were able to gain access to an area that has never been explored before. And we found all kinds of creatures. A lot of them they've seen before, a lot of them has been cataloged, but we have an entire tray of creatures that the scientists have not seen here before. So this is all very exciting. That's why you hear all the commotion going on.
Some coral. Coral. Oh, coral. We found some coral. Arctic coral.
Oceanographer Joanie Ferland explains that this is the largest discovery of marine life she has made in these Arctic waters.
It happened we arrived right in the blooms. So the production and the biomass was really high. Even in the plankton that we saw on the far leg going on, we gathered a sample and we took pictures of big chains of diatoms. It was gorgeous. So that was, out of my 5 year, the most productive spot. But it's not, it's just because of the timing in a year we were there. So that was really, really great.
Well, the reason we've stopped is because we've reached our next station. What the scientists are planning to do here is to identify the location of magnetic north. While the North Pole is a fixed position, the North Magnetic Pole moves several kilometers per year. So for navigational purposes, it's very important to continually identify and log its position. Just prepping the helicopter now and getting ourselves ready with life vests, etc. And we'll be leaving shortly. Banks Island is the 5th largest island in Canada and the 24th largest island in the world, with a population of only 115. Interestingly enough, one of the first explorers to discover the North Magnetic Pole was none other than Roald Amundsen. Do you find it cold here?
I'm well dressed. There's no bad weather, just people that are not well dressed.
So Mark, what are we doing? What are we doing out here with the guys?
All right. We're at just a sec. The winds have really picked up from when we first landed here about 2 hours ago. And those excessive winds are wreaking havoc with the experiments being done by the team from ArcticNet. They were calibrating some instruments to detect where north is, basically, because magnetic north is not the same as geographic north. Directly behind me is geographic north, and to my left over here is magnetic north. So they're calibrating these instruments that are very, very sensitive in order to determine the difference between the two. And they're having their troubles as well, battling this wind.
Mr. Mark Terry, it's a sunny day, it's a beautiful beach. Are you going to swim?
Graman, tabarnak.
T'as pas fait TV, là?
M'en fous.
OK? Pas pas mal en ligne.
So after 3 hours of hard work under trying conditions, the scientists were successful in pinpointing the current position of magnetic north. We're now very much looking forward to getting back to the ship for a well-deserved hot meal. It is cold today. It's about -9. Wind chill factor makes it feel like -20. But it's not that cold for us, right? Surprisingly, only 2% of the Arctic seabed has been mapped. To do this, sonar is used, and as is the case with any exploration of uncharted territory, some fascinating discoveries are made. One of the first significant observations made on our expedition was of an unusually long ice scour. An ice scour is actually a scratch made on the ocean floor by moving icebergs. To explain how the mapping process works, and also to take a look at this unusual ice scour, we talked with multi-beam operator Pim Koos.
The multi-beam is the main instrument we're using, and it measures the depth not only right below us, but also in a fan just starboard and port side of us.
Geospatial data technologist Eric Patton explains his discovery of one of the largest ice scours ever found during his mapping of the Arctic seabeds.
We found some amazing ice scour features. These are features on the seafloor that are essentially carved by the keels of ice sheets, and some of them could be really young or really old, going back to the last ice age. So we found some magnificent ice scours that are about, I measured one that was 8 to 9 meters deep, which is just phenomenal.
While these impressive scours were created by massive chunks of ice, interestingly enough, they were detected in an area where no massive ice structures are currently found. One of the more interesting observations made during recent mapping was of a collection of enormous seabed ring formations, measuring 200 meters in diameter by 30 meters in relief. The rings were first discovered by Third Officer Lisa Earle.
Well, we were doing some sounding in the Arctic, and we came over a very interesting bottom feature, and they're basically just circles, indentations with raised centers and raised exteriors. So I called the captain up, and he came up, and we did a couple of passes over them to try to cover the area and see what exactly was there, and it was pretty interesting.
We found this in the Hudson Bay on the first leg, and we were just transiting from one station to the other, and then it disappeared on our screen, and they're round, circular features. We're not really sure what they are. They look like donuts, in fact, or donuts that are imprinted on the seabed. And so we went over them once. We turned around, went over like that. We turned around, came back, and mapped them again. Then we continued our transit. The geologists on board, they've had a look at it. They've never seen such a thing, and they can't really explain what it is. So it's a bit of a mystery right now. But that's actually why we're here, because every time we map, we find something new.
Okay, well, these are very unique features. What I think could have happened is that due to isostatic rebound, which is caused by a release of pressure on the land during the retreat of glaciers, the land comes back up. It springs up like an elastic, which can cause fractures in the rock, allowing gas to escape from underground, which flows through the seafloor sediments and could create these circular features. What's especially unique about these features is this central pinnacle, which is a bit of a mystery and something very unique. Could be a result of permafrost existing in the seafloor sediments here, and a slow leak of gas creating this central pinnacle within these circular features. There's several types of gas that it could be. One could be methane hydrates, which are found in the seafloor, especially at depth and in colder regions. It's essentially frozen methane ice, and it has been known to, when exposed to seawater, thaw catastrophically and create large upwellings of that gas. And methane's a greenhouse gas, so that is some significant environmental concern.
This is day 6 right now, and we've entered some icy waters, but also a little rougher water too. We have 10-foot swells behind me here, and the wind has really picked up, which is causing for the water to move quite a bit. You'll notice that there's lots of new ice forming here, and it's getting quite crowded. That's why the ship is pitching a bit. This is actually very good to see, because most of the seas we were in, right up until this morning, were virtually ice-free. So we're seeing quite a good accumulation of new ice right now.
Since we're now encountering steady ice formations, the scientists are starting to deploy ice buoys. The buoys are robust measuring devices, crucial in sea ice research, as Dr. Bruno Tremblay explains.
So on this leg of the expedition, what I'm interested here is we deploy sea ice buoys within the Canadian Arctic archipelago. So those buoys measure sea ice thickness, they measure sea ice internal temperature, sea ice position, they measure also the internal sea ice strength, and basically all of this together allows us to actually derive the mechanical properties of sea ice. And these are things that we need to know in order to develop models and get better prediction of what the sea ice cover will look like in the future. So what we did was, in the Viscount Melville, we deployed 3 of these buoys on one floe. The buoy are giving us the data like hourly via satellite, and so we can analyze the data. And then life, and the buoy life is about 3 years. But every year we come to the Arctic and we deploy new buoy, and we also try to service like previously deployed buoy, repair them, like change batteries and things like this to extend the life of these buoys.
We have now entered an area of much older ice and larger ice sheets, as you can see from the blue coloring of the ice. This is the first opportunity we've had to make a landing on the ice to plant an ice motion beacon. There is always a potential risk in making a landing on sea ice. Thin spots, polar bears, but this spot was chosen due to its safety. The ice appears to be thick and solid, and the crew will keep a constant lookout from the bridge for any bears that might show up.
All right, so we're in a une cage de cochon. Oui, c'est correct? Okay, that means a pig cage, and us little piggies are being dropped from the ship onto the ice. And we're going to be placing a beacon that measures ice movement, and that's our mission now. So we're just heading down now, about to make our landing on the ice. If you look over there, you can see how loose the ice has been broken up by the ship. Careful with your step here. I stepped over there and went through water, okay?
Okay, well, we're standing here on a piece of second or third-year-old ice. We're on a nice little hummock here, so we've got a little elevation above the rest of the mean ice level. I've drilled a 20-25 centimeter hole, and I'm going to be putting an ice motion beacon into this hole and activating it so we can keep track of this flow as it drifts throughout the winter and into the summer.
What's going on?
Here, tell me, quickly. Leave it here.
It was a little embarrassing, but clearly we overreacted. Bears were indeed spotted from the ship's bridge, but they were quite a few kilometers away and we were in no danger.
That's you, hold on the stick.
The ship blasted its horn to send the bears in the opposite direction, so we regrouped and continued our interview with Matthew.
Okay. Yeah.
Well, we drilled the hole. We made sure it's pretty clean of snow. I take my little prepackaged ice motion beacon here. Now, they've made these things really easy to use in the field. You drill your hole, you put it down in the hole, you take off this magnet, which effectively is the on-off switch. So this guy's on now. So I expect in about 2 hours to hear my first message from this.
And it will remain here until about next August, approximately 10 months. And during that time, remote signals from the device will be relayed directly to the labs at the University of Manitoba, so they have a very good idea of how quickly the ice is moving and to what degree it's moving as well.
And over time, this will freeze in place, nice and solid. Our only concern, really, we're far enough from the ice flow edge, but I'm touching this. And if there are any bears in the area, they might smell me and come over here and go, oh, what is this thing? And they might start gnawing on it. So we'll have to hope that doesn't happen.
Well, it's day 8 now, and we're approaching the end of our journey. We've crossed the Northwest Passage and have traveled north to latitude 74. Ellesmere Island's on one side and Greenland's on the other. And it's here where we finally encounter the icebergs we'd expected to see long before now. These bergs are majestic in size, beautiful in shape, like floating sculptures in a gallery that few people ever visit. As beautiful as these icebergs are, their scarcity is a reminder of the dangers inherent in the melting ice here. I wonder if the same thing is taking place in Antarctica. While there are more icebergs, one can't help but notice a changing landscape not usually associated with the coldest continent on Earth. Temperatures well over zero are now common here during the summer months, and the melting land ice along the west coast is making a steady and increasingly significant contribution to sea level rise. In particular, one glacier here is a cause of great concern. At latitude 74.1 degrees, we find the largest ice drainage basin in the world, Pine Island Glacier. Despite its name, there are no pine trees, and it is not an island. As one of the world's largest and oldest glaciers, it measures 250 kilometers long and 2 kilometers thick. Recently, the British Antarctic Survey launched an unmanned submarine to track the floating portion of Pine Island Glacier. It traveled for 94 hours, covering more than 500 kilometers of the glacier's overhanging ice from underneath. The sub found a 300-meter high ridge formed by the floating end of the glacier. Deep, warmer water was passing over the ridge and entering the gap between floating ice and the ridge top. This, in turn, is causing Pine Island to melt from underneath. Glaciologist Dr. Adrian Jenkins explains this phenomenon.
Of course, as the clearance between the ice, as the ice thins, and the clearance between the ridge and the ice grows, there's more room for the warm water to get through. So there's another potential feedback whereby thinning of the ice allows more of the heat through across the ridge, which allows the ice to thin further, which allows more heat in.
The melting from underneath has accelerated the decline of Pine Island Glacier, and according to NASA, it has increased in speed to the rate of 1 foot an hour. The British Antarctic Survey believes that should the ice of Pine Island and its neighbor Thwaites Glacier melt completely, it would cause a rise of 1.5 meters, or nearly 5 feet, to global sea level. And according to NASA, if the entire west coast of Antarctica were to melt, sea levels would rise by as much as 5.5 meters, or 18 feet. There is no way of telling for sure just when the tongue of Pine Island will collapse, but when it does, it may very well look like this. This is the Petermann Ice Island. Currently floating in the Arctic Ocean near Hudson's Bay, this chunk of ice is too big to be called a mere iceberg, so it is referred to as an ice island. Formerly belonging to the Petermann Glacier on the west coast of Greenland, this section of ice represented 1/4 of the entire glacier's size. When it broke free on August 5, 2010, it was one of the biggest pieces of free-floating ice in polar history, measuring 5 times the size of Manhattan. Back on the Amundsen, Dr. Bruno Tremblay explains how glacier collapse like this is a significant threat to rising sea levels.
Sea ice is in the ocean. When it melts, it actually does not have much of an effect on the sea level. But when you have ice on land, like in Greenland, when you actually have calving of iceberg or ice shelf breaking, like in this case, then this contributes to the sea level rise. The Petermann Glacier, like it's a valley glacier, so some of the ice was already in the water, so already displacing a certain volume of water. So that fraction of the ice will not actually cause sea level rise, but a fraction of it will actually, because some of the ice was also coming from land further upstream, and that was ice that was on land, which is now in the water, and that it actually contributes to sea level rise. We expect in the future, if there's a big potential there for Greenland, like 6 meters of sea level rise, if it were to melt completely. So basically, we've seen that happen in the past. Like when we look at paleo record, like of the distant past, we've seen like large discharge of ice from Greenland. So we know it happened in the past. We know it can happen again in the future.
We're talking about several gigatons of water put back into the ocean. It still represents a drop
compared to what would happen if the whole Greenland ice sheet was melting. But it's still putting fresh water and contributes to lower the salinity of surface water.
Now, it's now clear to me what the message is we need to bring to delegates attending COP16. The greatest threat to mankind with respect to climate change is the collapse of these freshwater glaciers and the dangerous contribution to accelerating a rise in global sea levels. There always has been concern over the vast amounts of melting ice from the polar regions, but the threat is heightened dramatically when large chunks of this ice is suddenly added to the equation. The resolution we will lobby for will be a call to action for the nations of the world to jointly support the building of flood defenses for the vulnerable coastline communities, who will be the first to experience the devastating effects of rising sea levels. We will further ask for global support to relocate those communities that may experience more severe impacts. I feel we have some convincing evidence to bring to the Cancun conference. The cautionary and authoritative words of the scientists, as well as dramatic footage of one such glacier collapse. But as compelling as this evidence is, will it be enough to convince the delegates, negotiators, and world leaders? The whole point of this film isn't just to get people to watch a movie about climate change, it's to get people to do something about it. How much impact will our film have? We'll have to wait and see. Well, ever since we got back from the Arctic, it's been go, go, go. You know, it's really strange to go from a sub-zero climate to a tropical climate in just a few weeks. But that's exactly what we did, having arrived in Cancun for the United Nations Framework Convention on Climate Change. And I'm also very fortunate to have my co-producer, Jordana Ahrens, join me on this trip. Well, to be honest, despite our jet lag and general lack of sleep, we both feel invigorated now that we're actually here. I really feel that the discoveries covered in our film are going to have a powerful impact on the delegates attending this conference. So far, we screen the film every day, and it doesn't look like it's going to let up, and that's great, because I feel the more our message gets heard, the better chance of a resolution being drafted. The main message that we're trying to deliver here at COP16 is that the melting land ice, both in the Arctic and Antarctica, is going to cause a rise in sea levels. And that's going to create flooding and tsunamis throughout the world, especially affecting the coastal communities. And that's why we are hoping to see a resolution passed at this conference that actually calls for flood defenses to be built in all the coastal communities around the world, especially the ones most vulnerable. So thank you very much for allowing us to show this film and pass on that message. Now we have to wait. Now we're hopeful, due to the overwhelmingly enthusiastic response to our film, that something positive will come from this. But right now it just feels like we're waiting for the test results to come back from your doctor. There's just that nervous period of time that seems endless. While we didn't get the specific call to action we were looking for, we did witness something remarkable. The conference did, in fact, introduce a resolution. COP16's Enhanced Action on Adaptation now includes an official call to the world to work together to protect its coastal communities from rising sea levels. And what this resolution also reveals is that through countless hours of dedicated research, personal sacrifice in sub-zero climates, and long periods of time away from families, the voices of the scientists have indeed been heard. The journey continues.